Okay, let us start this last session of today. So I'm Shumilan from Indian Institute of Science, Bangalore. Here I'll be chairing this session. So we have two talks. First talk will be given by Professor Arti Garg from Shaha Institute of Nuclear Physics, Kolkata. And she'll be talking about nature of many-body localization transition.
Thanks, Shumilan. So let me start by thanking the organizers, especially Arnab, who is not here currently, for putting up this wonderful meeting. And also thanks to ICTS for providing the platform where these kind of meetings can be arranged. So I'm going to talk about MBL, and I guess we already had a lot of hot discussions about MBL in this meeting. So I'm going to present, what I'm going to present is from a very different perspective. So I'm going to talk about the nature of delocalization to many-body localization transition through the lens of single particle excitations, which we have calculated in highly excited many-body eigenstates of interacting quantum systems in the presence of random disorder as well as quasi-periodic potential. So most of the work that I'm going to present has been done in collaboration with Atanujana, who is a student at NISER Bhubaneswar, Ravi Chandra, who is a faculty there at NISER Bhubaneswar, and some last bits of work have been done in collaboration with Prasad, who was a postdoc at SINP in my group, and these are the references. So this audience, of course, there is no need to introduce the concept of MBL. It is already well explained in various talks. So I'm going to start with the main question that I'm going to address in this talk. So the main question of interest is, what is the nature of many-body localization transition? So this many-body localization is a very peculiar phase. It is, you start with a generic interacting quantum system and turn on disorder, you can make it insulating. So the question of interest is, how do you characterize this puzzling insulating phase, and how can you understand the nature of transition from delocalized phase to many-body localized phase? Now, why is this transition so puzzling? On one side, we have extended ergodic states which obey volume law of entanglement entropy. On the other side of this transition, we have non-ergodic localized states which obey area law of entanglement entropy. Also, it is not possible to think of any local order parameter which we generally use to define phases around a phase transition conventionally in statistical physics. So this MPL transition, which basically includes many highly excited energy states, does not follow classification scheme that we are familiar with for phase transitions from conventional statistical physics. So how can one make progress? So one needs to look for certain criteria that can help in hinting towards the nature of the many-body localization transition. And one such transition was given way back in 1986 by these four smart people, where they said that, and I'm going to call this criteria CCFS criteria. What these people said is, if you consider a system with quench random disorder, if it undergoes a transition, continuous transition with correlation length diverging as a power law at the transition point, then the critical exponent with which correlation length diverges must be greater than or equal to 2 by d, where d is the physical dimension of the system. So this is irrespective of the fact whether the clean system has any transition or not. So it's a very strong criteria which was developed only on the basis of probability distribution of random variables which are used to characterize phases in systems with random disorder. It does not assume anything about the quantum or classical nature of the system under consideration. Also, it is not necessary to know whether the system under consideration is or the transition under consideration is in equilibrium or out of equilibrium. So the only thing that is important is that you have a quench random disorder, and if the correlation length diverges as a power law at the transition point, then the critical exponent must satisfy this condition. So this is a much stronger criteria than the original Harris criteria, because Harris criteria provided only the stability condition for a phase transition that happens in a clean system, And if nu is greater than or equal to 2 by d, then the disorder is irrelevant in RG sense. So in this sense, CCFS criteria is much more stronger than the Harris criteria, although many times people quote CCFS criteria as generalized Harris criteria. So one should expect CCFS criteria to hold for systems like many-body localized system, where you have a transition as you tune the disorder from weak values, small values, to very large values, and you go from delocalized phase to many-body localized phase. Sorry? No, it doesn't matter. So the only thing that they didn't consider any specific state of the system. Okay, the statement is only if the correlation length is diverging, the critical exponent has to be greater than or equal to 2 by d. So it's simply coming from the central limit theorem. And CCFS criteria has been shown to be satisfied for Anderson model in 3-dimension and higher dimensions, as you can see here, that the exponent extracted from numerical analysis of level spacing ratio and some properties of the eigenfunctions always satisfies the CCFS criteria for non-interacting Anderson model. So one should expect that such a criteria should also work for interacting disordered system, and that is of interest to MBL. And indeed, some of the earlier real space RG calculations, which were phenomenological because we didn't have any microscopic RG calculations available, based on the finite size scaling of coupling between various local blocks, they could show that the critical exponent is of the order of 3. So it basically satisfies CCFS criteria. But this was the early set of RG calculations in context of MBL. Okay, so far so good. But if we look at the finite size scaling of various characterizations of many-body localization, like level spacing ratio, bipartite entanglement entropy, or bipartite fluctuations in system, what was found shockingly is that most of these analyses, most of these quantities give a critical exponent which is much less than 1. So all of them violate CCFS criteria strongly. It is nowhere close to 2. So all these studies were performed for one-dimensional chains of spinless fermions or spins, disordered spin chains. And what they found is that if they assume that the correlation length diverges as a power law at the transition point, then the critical exponent is always much, much less than 1. Some of the earlier studies found the critical exponent close to 1, but later on with a more controlled analysis of the quality of the scaling collapse, it was found to be actually around 0.6 or 0.5 for level spacing ratio. So there is, of course, a disparity between what was shown by renormalization group calculations, what is expected on the behavior of on the basis of non-interacting Anderson model, and what is seen in the numerics for disordered interacting systems. So what can be the reason? Of course, the system sizes one is dealing with in this exact diagonalization calculation is very small. So maybe the system sizes are so small that it is not giving us an answer which is consistent with the RG calculations. Or other possibility is that the correlation length actually does not diverge as a power law at the MBL transition point. And that's what was proposed based on modified RG calculations, which were based on so-called avalanche scenario, and they proposed a kind KT type transition at the MBL transition point, where the correlation length does not diverge as a power law, but has a different dependence on disorder. And there were a couple of numerical calculations where KT scaling was cross-checked for disordered interacting systems. And what was found is that the transition point itself scales with the system size, which created a lot of confusion about whether the MBL phase is stable in the limit of infinite system sizes or not. But then we also have a few exceptional cases where finite size scaling of level spacing ratio and diagonal entropy shows consistency with the CCFS criteria. So this is basically to show that there is a lot of confusion in the field, although based on the finite size scaling of non-interacting Anderson model, one would expect that something like CCFS criteria should work for many body localized system as well. And some of the RG calculations also showed results in consistency with this expectation, but most of the numerical calculations did not show CCFS criteria getting satisfied. So with this background, what I'm going to talk about today is why don't we look at some different physical observables which live in the physical space of the system, which don't live on the Fock space. Okay, so with this motivation, I'm going to talk about many-body localization transition through single particle excitations. These are the objects which we always deal with in condensed matter systems like regular metal insulator transition, condensed superconductivity, etc. So why don't we explore the MBL phase also through single particle Green's function? And before I go into the detail of my work, let me first share with you what are our main results. So we calculated single particle Green's function in highly excited many-body eigenstates of disordered interacting quantum system. And what we find is that single particle excitation provide an ideal metric to characterize the delocalization to many-body localization transition. These excitations are extended if you are in the weakly disordered phase, but in the many-body localized phase, excitations are localized and long-lived. So if you calculate the typical value of the local density of state from these Green's function or the scattering rates, which basically tells you the lifetime of these single particle excitations, you will see that the typical value of local density of state act as an ideal order parameter being of finite, which is finite in the delocalized phase, but since the excitations are localized, it vanishes in the localized phase. The typical value of local density of state vanishes in the localized phase, and same thing happened with the scattering rates. And if you do the finite size scaling of the ratio of typical to average value of local density of state and scattering rates, what you, with the assumption that the correlation length diverges at the transition point, you find that the critical exponent satisfies Harris criteria if the on-site potential in the system is a quench random disorder. But if you consider the case of quasi-periodic potential, then of course it does not satisfy the CCFS criteria. CCFS criteria is not supposed to work for deterministic potentials. And in the case of quasi-periodic potential, we find that the critical exponent is greater than or equal to 1 by d. Sorry? Yes. Oh, sorry. It should be 2 by d, right? It's just 1 by d. Okay, so this is the model that we studied. We looked at the model of spinless fermions with power law interactions. So we looked at various range of interactions, and this is the on-site potential. So we looked at the case of random disorder as well as Aubrey-Henry potential. And the quantities that we look at is we defined a Green's function in the nth eigenstate. So it's basically a propagator which is calculated in the nth many-body eigenstate of the Hamiltonian. So you create a particle at t equal to 0 at some site j. What is the probability of finding the particle at a later time t at site I? So generally these quantities are calculated either in the ground state or in some thermal ensemble average at some finite temperature T, but because of the problem that we have at hand, we calculated it for every eigenstate in the system, and imaginary part of the Fourier transform of this Green's function gives us the local density of state at frequency omega. So this is the frequency for single particle excitation, and n is the label for the many body eigenstate with respect to which we are creating the single particle excitations. So one can also define a generalized Dyson equation where a self energy for every nth eigenstate of the system can be calculated using the inverse of Green's function matrix for the non-interacting case and the Green's function matrix for the interacting case. And again, imaginary part of this self-energy gives you the scattering rate for single particle excitations, and inverse of this scattering rates gives you the lifetime of excitations. So so let's suppose we switch off the interaction and look at a simpler limit of the model that I showed you, where we just have a random disorder and some kinetic energy, some hopping for the fermions, spinless fermions. Then this is a very simple calculation. The local density of state depends on the wave functions in real space in this simple manner, and this has been studied for ages for Anderson localization. And since the wave function is exponentially localized at the point, since the wave function decays exponentially from the point where it is localized, the density of state is very small at most of the points in the lattice, and because of which, if you calculate the typical value of the density of state, it is very small in the localized phase, but the average value of the density of state is still finite. Okay, because you are creating a single particle excitation, so that has to live somewhere. So average value of the density of state is finite, but the typical value of the density of state is very small, and this is also reflected in this asymmetric log normal distribution as the disorder strength increases. Now coming to the, this slide is not very important, so let's see what happens when you turn on the interactions. So when you turn on the interactions and again calculate single particle Green's function for this system, the first thing one needs to look at is the probability distribution of local density of states and scattering rates. So for weak disorder, you can see that the typical value of the distribution and the average value are close to each other, although the typical value is already a little smaller than the average value. And a numerical fit to the data shows that this distribution is close to log normal distribution. As you increase the strength of disorder, more and more weight shifts towards the smaller values, which means that the typical value for local density of states as well as scattering rates decreases. What does it mean? It basically means that as you increase the strength of disorder, your single particle excitations are becoming more localized. Okay, that's what is indicated by a reduction in the value of the typical value of local density of states. But the reduction in the value of the typical value of scattering rate means that the lifetime of these excitations increases. So in the MBL phase, you have highly localized excitations which also have very long lifetime. This is for nearest neighbor case. Yeah. So first I'm showing the data for nearest neighbor case, and then I will discuss the power law interactions. So now suppose we look at the ratio of, this earlier distribution has already shown you that it's not sensible to look at the average value of this local density of state and scattering rates to analyze the delocalization to localization transition. The typical values of these distributions provide you a meaningful quantity to distinguish between the two phases. And that's what we do here. So we look at the ratio of typical to average value of local density of state at frequency close to the Fermi energy of the system. And these excitations were produced in the middle of the band. So basically you look at only some of the highly excited many body eigenstates in the middle of the spectrum, create the single particle excitations, and calculate this rho typical and rho average, and similarly here. So for very weak disorder, you can see that the ratio is of the order of 1, which means that excitations are pretty much extended, and as you increase the strength of disorder, the ratio decreases, but still for these small values of disorder, the ratio increases as the system size increases. Okay, it means that as you go to very, very large system sizes, it can become of the order of 1 in all these parameter regime. But beyond certain value of disorder, we don't see any significant dependence on the system sizes in this ratio of typical to average density of state. And a very similar feature is seen for ratio of typical to average value of scattering rates, again calculated close to the Fermi energy. So basically the typical values go to 0 much faster than the average value in the strongly disordered limit. So far I showed you the single particle excitations created only close to the Fermi energy, but one can create single particle excitations even far away from the Fermi energy. So this is the plot where we are creating single particle excitations again in the middle of the many body eigen spectrum, but the frequency can vary to whatever it is allowed by the spectrum. So you can create single particle excitations even away from the Fermi energy. And if you look at and here we are showing what happens if you change the energy of the many body eigenstate with respect to which you are creating single particle excitations. So of course it is easiest to create extended excitations in the middle of the band where the many body eigenstate itself is extended. But if you go to the edges of the many body spectrum, you see that the typical values of local density of state and scattering rates are much smaller there. It means as you increase the disorder strength, the single particle excitations first get localized for many body eigenstates at the edges of the spectrum, and you require much larger disorder to localize single particle excitations in the middle of the spectrum. So this is just to convince you that these quantities basically capture all the features that we need for a legitimate characterization of delocalized phase and the ambial phase. So now we turn on the power law interaction and look at what happens as you turn on the effect, as you look at the longer range interactions in your system. So if you fix the strength of disorder and increase the range of interaction, you will see that the typical value of local density of state and hence the scattering rate reduces. So basically we see a stronger effect of disorder and a stronger tendency for localization if the range of interaction is larger. So one has to be very careful here when I'm saying range of interaction is larger. It's only the interaction among fermions which is larger, but the hopping is still nearest neighbor. Okay, and a similar conclusion has been obtained from study on disordered spin chains, where only the ZZ coupling between the spin was considered to be long range, but the spin flip terms were short range. So as long as the spin flip term is short range, you always see that MBL survives in the presence of long range interactions, at least in finite size systems. And in fact, you also see a stronger tendency towards localization if the range of interaction is longer. Okay, of course, there are very strong finite size effects. We are limited by the system sizes, but I'm showing you whatever we see within the best system size that we can explore within ED. Well, I'm considering the model of spinless fermions. So the interactions, it's only the repulsion between fermions. But the hopping is nearest neighbor. Yes, but the statement about spin flip was based on an analogous study in disordered spin chains, where MBL was seen if the ZZ coupling was long range, but the spin flip coupling was short range in nature. Okay, so just a slide for those who are used to thinking in terms of strong correlated physics. So generally we talk about adiabatic continuity when we talk about metal insulated, weakly interacting metals like Fermi liquid and all.
So, sorry, just one.
Where?
Yeah, here, just one question.
Okay.
In the previous slide.
Yeah.
So when alpha is approaching 0, what happens? I mean, from the positive side?
We cannot study that small value of alpha.
No. So can you go back to your Hamiltonian?
So as you reduce alpha, the range of interaction increases.
Yeah, can you go back to your Hamiltonian? So it becomes almost all-to-all coupling, right?
Yeah, it becomes almost all-to-all coupling, and I think there was a study by Sitadi and David Logan because they did some mean field kind of calculation for the Fock space propagator. And
okay.
So there it can be worked out, but if you're numerically calculating, we didn't look at alpha smaller than half.
Okay, thanks.
Yeah, I mean, that's what it looks like from the finite size calculations that, and I think one reason is that if you, the way this long range interaction enters in your effective Anderson model is, it only changes the distribution of your local energy in the effective Anderson model. And the way that distribution changes is such that even at weaker disorders, you see a stronger effect of interaction localization. Okay, so just a side comment on adiabatic continuity. It looks like the strongly disordered interacting systems have a stronger notion of adiabatic continuity. So we see single particle excitations which are long-lived in strongly disordered MBL phase, even at very high temperature, not only at the Fermi energy, but even far from it. So this is to some extent consistent with what was proposed by Anderson long back in 1970, where he said that there can be a disordered interacting phase, which he called as the Fermi glass, which can have localized excitations, and it should be adiabatically connected to Anderson insulator. But this idea about Fermi glass remained elusive for many, many years, unless we started working on the MBL phase, where it was already shown in first work by Basco and all that there can be very long-lived sharp excitations in the MBL phase, as long as the interactions are short-range in nature. And what our numerics indicate is that probably it's possible to have long-lived sharp excitations even in the presence of long-range power law interactions in the MBL systems. Okay, so now I hope all of us agree that single particle excitations provide us an ideal characterizations of the delocalization to MBL transition. So now we try to understand the nature of MBL transition using these excitations. So we looked at the finite size scaling of the physical observables that we get from the single particle Green's function, mainly the local density of state, the ratio of typical to average value of local density of state, and the ratio of typical to average value of scattering rates. And we calculated the cost function to control the quality or to get the quality of the scaling collapse. So the minimum of the cost function is actually supposed to tell you the transition point and the critical exponent. So we assume that the correlation line diverges is a power law, and then we did the finite size scaling with that assumption. And as you can see in this cost function color plot, which is plotted in this nu and WC plane, that the minima occurs, so a proper minimization procedure actually gives you a very flattish, broadish minima for the cost function. So WC has a broad range somewhere between 7.1 to 7.9, and the critical exponent varies from somewhere between 2.1 to 2.7. So if you choose a value of WC and nu anywhere in this range, you get a good quality collapse. And here for the purpose of illustration, we have shown the collapse for WC equal to 7.3 and nu equal to 2.2. So you basically, for the nearest neighbor interacting system and random disorder, we see that single particle excitations gives you quantities which obey CCFS criteria. And then we looked at the finite size scaling of similar quantities for system with long range interactions, with power law interactions for alpha equal to 1 and alpha equal to 3. And again, as you can see that the critical exponent actually is always above 2. The minima of the cost function corresponds to nu greater than or equal to 2. And the transition point is somewhere between 7 to 7.9, and nu is somewhere between 2.3 to 2.9. So for the purpose of illustration, we have shown the collapse plot for nu equal to 2.5. So even in the presence of power law interactions, it looks like the critical exponent remains almost in the same range, always satisfying the CCFS criteria. And even the range of WC is close to what you get from nearest neighbor interaction. So although we see qualitative signature of stronger effects of disorder in the presence of long-range interactions, but we don't see any shift in the transition point because our error bars are very large from the minimization of the cost function. Now, if we repeat the same analysis for the level spacing ratio, what we see is that a very different picture from the minimization of the cost function. We get a critical exponent which is around 0.64, which is consistent with many of the earlier calculations, which have shown violation of CCFS criteria in level spacing ratio. And the transition point is also smaller than what was obtained from Green's function quantities. So basically, what is the summary? So from Green's function quantities, we see a much larger transition point, although the error bar is pretty large. And from the level spacing ratio, we see a smaller transition point. Now, this kind of difference in transition point has always been known for MBL systems, because earlier also we looked at the time evolution of density imbalance, and then there was a lot of work by Soumya and Marlin and Ferdinand Evers, where they looked at the time evolution of correlation function and mean square displacement. And what was found is that the transition point obtained from dynamical quantities is always larger than what you get from the level spacing ratio. And I think it is to some extent consistent with what has been proposed by David Hughes, Vedika Khemani, and others, where they proposed so-called landmarks, which can be realized in finite size calculation of various diagnostics of MBL systems. So now coming to the difference in the critical point. So we see that the single particle excitations gives you a critical exponent which is consistent with CCFS criteria, but quantities like level spacing ratio have always given you a critical exponent which is much less than 1. In fact, we found, I don't know whether it is only a coincidence, but what we found is that the critical exponent from the level spacing ratio is very close to the critical exponent that was obtained for from the finite size scaling of Feinberg self-energy from Fock space propagator. So now there is a nice connection between the Feinberg self-energy obtained from the Fock space propagator and the level spacing ratio, because if you basically the poles of the Fock space propagator are nothing but the eigenvalues of your effective Anderson model on the Fock space. So if you're sitting in very strong disorder limit, then one can do a kind of perturbation theory in hopping for the eigenvalues of the Fock space propagator, and the 0th term will be just the diagonal disorder term that appears in the effective Anderson model. And then you have correction to that 0th order term coming from the Feinberg self-energy. So the eigenvalues of the effective Anderson model in very strong disorder limit actually is directly proportional to the Feinberg self-energy that you get when you calculate the Fock space propagator. So it should not be surprising that the finite size scaling of level spacing ratio and the finite size scaling of Feinberg self-energy from Fock space propagator gives you a very similar critical exponent. And now another point, does the critical exponent being so small really means that the CCFS criteria is violated? So the effective Anderson model does not live in the physical dimension d equal to 1 from where we started with. Our physical chain lives in d equal to 1 dimension, but the effective Anderson model, whose eigenvalues are used to get the level spacing ratio, lives on a complicated Fock graph whose connectivity varies from node to node. But for most of the basis states in the middle of the Fock graph, the connectivity is of the order of the system size itself. So if one tries to estimate the effective dimensionality of the Fock space and try to come up with the generalized modified CCFS criteria for any quantity that lives on the Fock space, then it should be nu greater than or equal to some inversely 1 by L. It should be of the nu should be greater than or equal to 1 by L rather than 1 by D or 2 by D for the where D is the physical dimension of the system. So what I'm trying to say is that maybe the quantities like level spacing ratio, they are obeying a modified CCFS criteria where the dimension, effective dimension or the connectivity of the Fock space enters into the CCFS criteria rather than the physical dimension D of the real system that we are starting with. And this is just a proposal. This is just an explanation I can think of that why the level spacing ratio does not satisfy the CCFS criteria. Of course, we also perform the KT scaling for all these quantities, And from KT scaling of level spacing ratio, you can get critical exponent very close to what you get from the diverging correlation length, but the cost function from KT scaling is always more than the cost function from the diverging correlation length. And KT scaling does not work for Green's function quantities at all. That also we have checked. So based on this, I think I would like to conclude that Green's function quantities satisfy the CCFS criteria as long as the system has quench random disorder, and it is true for any range of interaction if the hopping remains short range. Now just a last bit of piece where we also looked at system with quasi-periodic potentials. Now CCFS criteria is not supposed to work for deterministic potentials, but still it is good to see what can happen if you look at a system with quasi-periodic potential. Also, there is no generalization of luck criteria in the sense of CCFS criteria. So just like for random disorder, there is a criteria by Harris which tells you the condition for the stability of the transition in clean system in the presence of random disorder. There is a criteria by Luck which was given in 1993, where if a clean system has a transition, how stable that transition is to the presence of quasi-periodic terms in the system. And the condition for that is that nu should be greater than or equal to 1 by d. But this is not the condition, I mean, this is not a strong criteria like CCFS criteria because it's only telling us the stability condition. So it should not be used for MBL in the presence of quasi-periodic potentials. So we looked at the interacting Arbre-André model and performed the finite size scaling of level spacing ratio as well as the quantities that we get from single particle Green's function in highly excited many body eigenstates. And what we find is that the critical exponent from level spacing ratio is again very small, much less than 1. But the critical exponent from local density of state is of the order of 1.2. So it is less, it does not of course satisfy the CCFS criteria, but it is greater than 1. So I would just like to end at this slide where I have shown the comparison of random and deterministic models, that the critical point for the deterministic model is greater than or equal to 1 by d for single particle Green's function. But for, if you look at the level spacing ratio, one cannot really distinguish between the systems with random disorder and quasi-periodic potential because both seems to be in the same universality class if you look at the level spacing ratio. But if you look at more appropriate quantities like single particle local density of states or scattering rates, then one can see a clear difference in the universality class of two set of systems with random disorder and quasi-periodic potential. So these are my conclusions, and I think I will stop here. My time is up.
I was, in some of my work, I found it very helpful to consider nu as a function of L.
Sorry,
Have you ever, the reason being that as the system size gets bigger and bigger, there are different kinds of excitations, especially when you have a problem with the avalanche phenomenon, which might be relevant and move the actual apparent transition around. Did you consider adding that degree of flexibility to your measures of nu?
Yeah, so here you're saying the critical exponent itself to be a function of L, or what's your definition of nu here? I thought it was correlation length, that's what you told me yesterday.
Well, right, but you have a system of size L and you try to get some indication of what it looks like for the correlation exponent. And you might get different answers depending upon what L is. When you're doing numerical studies, for example.
Well, okay, so we have not really looked at it because with these limited system sizes, the only thing, already it is hard to extract nu which is independent of the system size. And also the way generally nu is defined is that if you take the limit L going to infinity, that should be the critical exponent. So we only used a constant value of nu independent of L and did the whole analysis.
Okay, anyway, I mean, that's something that is worth considering. Let's put it that
Yeah.
way.
Yeah. So when you say that, when you try to apply these ideas to a fog graph, then maybe the D that you put in the Harris criterion shouldn't be the real space dimension, but actually the coordination number on the fog graph.
Yeah,
Like,
I mean, I cannot prove it, but
no, sure,
that's
sure,
just a
sure.
thought.
No, I understand where that argument is coming from, but I guess another thing which happens on the fog graph is that the on-site disorder that you have is highly correlated.
Correlated, right?
So do you have any idea what happens to the Harris criterion when you normally have, when you have correlations among the disorder? Like I can imagine that if the correlations are if the disorder is in some sense positively correlated, then it makes the situation even worse because it's sort of easier for rare regions to nucleate, right, and destroy the transition. But here, of course, you can have, I guess, negative and positive correlations.
Yeah, so I guess as long as the central limit theory works, central limit theorem works to some extent, the criteria should not change much. But if the correlation is really strong, so we have not really checked for it. Okay, so
Right.
the statement I was trying to make is if we assume that the CCFS criteria holds, then at best what should hold for level spacing ratio
Right.
is a modified CCFS criteria,
Right.
where the Fock space dimensionality should enter rather than the dimension, physical dimension of the
Right.
system.
So the question I had, so does this enhanced stability to long-range interactions tell anything about higher dimensions? Think of a 2D
Okay.
square lattice as a 1D chain
I
with long
think
range.
it will be too big a jump to say anything about higher dimensions based on this work.
Other question? Okay, if not, let's thank her. Okay, so we'll move on to the next talk. It will be given by Professor Somo Bera from IIT Mumbai, and he'll be talking about internal clock for many-body delocalization.
Okay. Thank you, Shumilanda, and I also would like to start thanking the organizer for giving me a chance to talk in this very nice and stimulating conference. So yeah, so I will be talking about internal clock for many-body delocalization. I will mention and I will discuss what do I mean by many-body delocalization. So before I talk, let me thank my collaborator, Ishita Modak. She's a PhD student at IIT Bombay, and Ferdinand Evers is from University of Regensburg. And whatever I'm not going to talk about, you will find it in this reference. So actually, I would like to start by also saying what is the main message of this talk. And actually, it turns out that Lev already gave me the main message. And it was about that scale invariant dynamics emerges at mid-time. Yeah, and I will show you and I will try to convince you that it is indeed the case, that there are certain quantities that if you look at intermediate time scales, there are certain scale invariance that is emerging. And from there, we can understand a lot. Actually, what I'm going to talk about is essentially the following, and this is more or less my conclusion. So what Lev was mentioning, that there is this kind of a time scale, we call it Thouless time or ergodicity time or whatever, which goes at L squared times e to the power w with some prefactor and some coefficients with the w. What I will show you that I don't need to this particular form of this time scale, but that time scale can be reparameterized again in the similar word that I am using like previous speakers with the entanglement entropy itself. And within this reparameterization, I will tell you that there are certain scale invariant dynamics that emerges at least in the ergodic phase, and then one can push it towards the localized phase, which is all of us knows. Good. With this small introduction, let me already show you where it emerges. So we all know about entanglement and thermalization. At least in this conference, this is the simplest thing. So that's our usual von Neumann bipartite entanglement entropy. Rho A is the density matrix of the half system, and that's my entanglement entropy. In the limit, when the system is thermal or maximally chaotic, what we know that it reaches the page limit. Yeah. In the also, we ignore certain corrections. And this is a quench that I will be mostly talking about. Sometimes if something else I'll talk, I'll mention. But during the quench, what you see here is essentially starting from a very low entangled state, it quickly grows. So this is in a log-log scale. It's a usual model, XXZ spin chain in one dimension. And what you see here is a very quick increase, which is a ballistic increase. And then there is saturation. That saturation is a volume law saturation. And that is what this page limit is. So you have a volume law correction, and here the density matrix is half system. So it's a L over 2. But this is a finite system, and with a certain symmetry inbuilt here. So momentum is a good conserved quantity and many other things. That has certain corrections. It turns out there are log corrections here as well. And one can exactly see this log correction in this saturation time. What is alpha? This is infinity. So that is how much I am exhausting the page limit. So essentially it is 0.7 of the page limit, 0.7, almost similar to everywhere. And that 30% accounts for this logarithmic correction and certain conservation laws. Good. But what I wanted to show you that this parameterization. So if you start with this model, these plots, and if you parameterize the time with respect to the this saturation, or S infinity I call it, both in the y and the x-axis, what you see is a perfect collapse of these curves. And that's something we kind of knew already from one of the very early work by Kim and Hughes, that there is a way of parameterizing the time such that there is an universal curve that emerges, or universal dynamics that emerges in this type of ergodic models. And this will come handy as I move on. The second part of the puzzle is obviously localized phase. Again, this thanks to Arti, she already gave us a very nice introduction. So contrasting the ballistic situation in the localized case, so it turns out that, or at least the prediction is that it will be a logarithmic growth of entanglement. Okay. And it comes from the idea that there are localized integrals of motion, or let's say localized single particle eigenstate, and if you turn on the dephasing, you will immediately see that there is a logarithmic growth. And this been a main feature of MBL for a very long time, at least for last 10 years or so, but we revisited this. Let's look at, again, the same data as I showed you previously, but now in the presence of disorder. So I'll go slow. So I will first show you the data which is weakly disordered. So starting from this point, these are the data. What you see here is essentially the same type of experiment where I increase the disorder strength from 0 to 1.5, and another data which is for disorder twice larger, which is 3. For two different system size, one is 16, one is 24. And here it's plotted in a following way. It's a linear and the log. Okay. I do know that it will be a power law, but I don't want to see it in that way, but I want to see it in this particular way, because for me what is interesting is this curvature in this way of looking at it. Yeah, that curvature is actually telling you that there is a power law. Good. And more importantly, the larger system size curve more. So this is 16, this is 24, again this is 16, this is 24. That curvature survives now in the right-hand panel, where again the disorder has changed only. So it went from 1.5 to now 8. And what you have to notice here is that this left-hand curvature that I showed here is over here as well. Exactly in the same way that you plot in the lean log, and this curvature survives. It's small, but it's there. And that is my signature that up to this point, there is no logarithmic growth of entanglement. Rather, it's a log, maybe a lower bound. In particular, what we also have to note is that the increasing system size, it goes towards left. Yeah? So the larger system size is always in the left. And that gives you the larger curvature. No, everything is linear. So y-axis is always linear. Here it will be. Here you mean? That will be ballistic essentially. Here also it will be ballistic, here also I would expect it to ballistic. So the idea is that within the localization length, there will be a strong growth. You would expect it, but I am telling you that that should be at the longer time and it is not there. Yeah, so the log will be much longer time, yeah. And I am saying that within the simulation time that you see for a very large disorder, if you look at it carefully and not fit anything, there is this small curvature that always tells you that log is not there. Actually, if you believe in this, you can do the following.
Earlier data they fitted, you were saying they fitted that as a log?
Two things. The earlier data, at least the Jens data, was for weak interaction, weakly interacting system. So the interaction was 10 times smaller than this. So here everything is order 1. And obviously you can also fit a log over here, but then you will find coefficient which depends on system size that they had missed. Okay, second point. So if you agree with that alpha or the power law, you can essentially look at it in this following way. Without fitting, you can look at the log derivative of the entanglement with the log of time, plot it as a function of entanglement just to see how far you have reached. And what you see is the emergence of a plateau. So color is same thing. So this is for 4, this is for 6. What you see is a small plateau. Again, with increasing system size, everything goes up, which means that the power law will form with larger and larger system size as you increase the time as well. So this is exactly one thing that I will again come back, that the entanglement can be used as a function of time. So it can be replaced or reparameterized. There are many comments I can make, but the small thing I will talk about is the following thing. There is what is known as particle entropy now, which has been very popular. And if it is the case that, or at least here it is the case that the log is not compatible with this data, then log t, which is one would expect for the particle entropy, is also not compatible. I'll leave it at this point. Okay, so that's all about entanglement, and this is what we call creep. Yeah? There is a slow growth, and one is to just look for this slow growth. And I will show you other examples where this slow growth also appears. It's not this only entanglement, but many other places. So to be precise, here is the model that we'll be looking at. The usual XXZ chain is written in the Fermion language, but it's the usual one. One looks, and I'll look at the density correlator at 2 point and 2 time. So that's essentially the transport of the charge. And in particular, I'll look at the second moment. Okay, what I expect for a diffusive model, that it has a Gaussian shape. It has a width, and that width increases with t to the power half, and that half is a signature of the diffusion. Whereas at the same time, the return probability, or at the point of 0, 0, so x being 0, you would expect it to go down with the same power law, which is half. So just to show you data, so this is very old data, but doesn't matter. Again, to show and to point out the creep. So here is the delta x as a function of time. So that line that you see over there is the v equal to 0, no interaction. So that's the Anderson localized phase. Therefore, delta x doesn't increase, so it just stops. This wave packet that I showed you is just stopped. Whereas with increasing disorder, with increasing interaction, what you see is the growth of this delta x. And again, what I show you here is not the weak disorder, but the large disorder, where you would expect to have an MBL, but you always see this creep. And this creep is a manifestation of many other things, but essentially mixture of ergodic and non-ergodic grain, and I will come to it in a second. But that's what we always see. Yeah? So that creep always exists, no matter whether you look at the random model or at the O'Brien model, the feature is same. And if you look at the MBL from this perspective, this creep, I don't know whether it saturates over here or not, but at least within the finite size system that we do, seems to suggest that there is no MBL, at least in this parameter regime. All order 1, everything always order 1. One, exactly 1, yeah. Okay, so actually the figure that one sees in this kind of density correlator, I already said that if it is a diffusion, we would expect a Gaussian. But in this particular case, we never see a Gaussian actually. If you look at the full distribution, you always see that this dashed line is a non-interacting one. So you would expect that in the non-interacting case, these are localized, so it's exponentially localized. So that's a log scale, this is a linear X scale. In any values of disorder, we do see that this is almost close to the non-interacting value. Yeah, so it is almost looks like a tent type of feature, but never a Gaussian. Let me not go into the details of it, but more or less by analyzing such a data, you can come up with such a phase diagram. So the clean fixed point is essentially a super diffusion. That's the KPZ scaling. As you increase the disorder, there are accelerating dynamics. We call it transient subdiffusion. Indeed, the exponent is less than half, but it never saturates. There is a strong finite size effects. With larger disorder, we see slow dynamics. We call it decelerating dynamics, but it's also creep. Beta is almost close to 0. That is this 0.1 I mentioned, but there is still dynamics left out. There is even further down, maybe there is a true MBL or not, I don't know, but the current numerics does not support it. Okay, just to, for the younger audience, this is kind of a summary of what has been gone through to this field. It has matured a lot. So initially, so these are all representative figure. I have nothing against anyone. And this is essentially early, or what I call first generation scenario, early 2014. We had eigenstate properties like level statistics, entanglement, fluctuation, mostly used ED to get an estimate of the WC for this particular model that I'm mentioning, which is around between 3.1 to 3.8 all the time. Yeah. And the exponent was close to 1, which I think now Arti was saying that it may not be true over here. Second generation scenario, which is essentially between 2017 to 2022, we kind of looked at dynamical properties, different type of correlators that I mentioned, imbalance, which was motivated by the experiments, entanglement using TDV, PT, BD type of things, and the WC increased a little bit by a 1.5 factor. Exponent didn't change. Over the last couple of years, the things have changed again. So people started looking at mixed properties, Bath class model, resonance models, level statistics again revisited, and again ED and many other things. But now the estimate of WC has gone really in a different direction. Almost its current estimate is even more than 20. Huh? I have no idea. But I want to give a meaning to this number. So one should understand what are these numbers actually. So if I want to look at again the non-interacting case, because that's my reference point. So if you look at the non-interacting localization length actually as a function of disorder, what you can see that the non-interacting localization length is already order 1 around the value of disorder strength W3 or 4. Yeah, and that tells you that that is already a very strong disorder for this system in one dimension. You don't need to go to 20 to see anything. So if we cannot see localization around these values of disorder, I do not know where it is, at least in the presence of interaction. You can also argue it from the density of states, of the single particle density of states, but let's not go into this. Okay, so we understand many things, but we also don't understand many other things like where is WC, what is the correlation length exponent, Loci MBL. A very interesting thing is about time crystals and many other things, symmetries, long range, higher dimension. The questions are plenty. This is, I would say, is the time to really work on this field. Is very exciting. And what I'm going to tell you that entanglement offers an alternate view, and essentially this mid-time view that Lev was propagating, or at least talking about in the morning. So the idea is already very simple. So I'm going to look at the imbalance. Yeah. Now that's the imbalance starting from a product state for the same model for a relatively weak disorder. I don't need to go to large disorder, relatively weak disorder, and as a function of time. And what I show here is 10 different samples. It's not averaged over. W1.5, I would expect no matter what, it's going to be ergodic. So everything should go to 0, and the definition of ergodicity in this particular case, for this particular observable, that I of t goes to 0. Okay. And what you already see over here for weak disorder, there is a strong sample-to-sample fluctuations. So there are samples which does not thermalize, whereas there are samples quickly thermalize. How do you deal with this? Yeah, so that's the first question that I want to understand. Now, the way we deal with it is the following, that we think that this time needs to be reparameterized because we believe that W1.5 must thermalize, but how do I see that it thermalizing? And the way I'm doing it is the following. Instead of looking at it in the lab time, the simulation time, I'm replotting the whole data in terms of entanglement itself. Okay, the entanglement I already defined, and I already told you that the entanglement can be a good quantifier for the time. So this is the entanglement itself, and what you see here is a shrinkage of the data, less fluctuation, in the following way, that the system or the samples which were going to kind of thermalizing very fast has a large entanglement, whereas the system that was not thermalizing at all has a much smaller entanglement. Essentially, what it tells you already at this level that you need to wait long enough for this system to go down and bend over there. And that is everywhere. Yeah, this is nothing to do with W1.5. So you go from W1.5 to 2.5 to 5.0, similar features reappears. Strong sample-to-sample fluctuation, strong sample-to-sample fluctuation in the growth of entanglement. Therefore, if you relook the data in this particular way, you see a very different picture than just saying that, okay, this is with time what is happening. Now, this is a single, it would have been nice that if all the curve would have collapsed once you do the entanglement, so then it would have been a very nice clock or a notion of internal time, but that didn't happen. So what happens is the average one. So this is essentially, again, the imbalance plotted as a function of average entanglement entropy divided by the page. So 1 is the maximum that it can go. So it's a finite number, 0 to 1. And this is the average imbalance. I need a fitting parameter, FL of W. Once I multiply that, what I see here that all the disorder value collapses in a single scaling curve. This is done for different system sizes just to show that it happens for any system size. And this time scales where it goes up to this point, that point, and previous also for other disorder value, it follows the same curve, kind of tells you that there may be an exponential scaling of the time with the W that has been proposed previously as well. Good. So this is kind of tells me that if I see a curve on this scaling collapse, I would say that this is a ergodic curve. Now, there is a drawback to this picture, and I will point it towards you that there could be a localization, and that would imply that there is no curvature. So you see there is a kind of a right-hand bending of this curve, and localization would imply that there will be a curve which will come and stop actually. So it will exhaust the page, whatever the final entanglement, but the imbalance should not decay. Yeah, so that would be the meaning of localization in this case, and that I call flow and stop a possibility, and I cannot completely discard it. Essentially, one can show it in the following way. So this is essentially a cartoon of a flow and stop. So imbalance can go and saturate at some finite value, and the entanglement can grow. Let's imagine this is a log, and then it kind of stops at the exponentially large time scales with some value which is also grows with volume. So that's the picture of entanglement. And if you linearize my collapse curve, you can show that this picture is consistent with a small imbalance decay as well. And indeed, Piotr and Kuba showed that there is a possibility of a small imbalance decay at very strong disorders. I'll not comment on the numerics at this point, but there is this possibility also, which I cannot discard at this point. Okay, so I'll change gear. I'll change gear and I will show you that there is another interesting aspect of it when you do not conserve anything. So I will talk about now a Floquet model, where I will be talking about energy absorption and essentially something called local temperature. So the model that I will be showing is the following, that it's a Floquet transverse field Ising model, where Hx is the longitudinal transverse field, and there is also a longitudinal field. The disorder sits in the longitudinal field, Gi, which is taken between 0 to 2 pi. Whereas it's parameterized with this some weird way, gamma. Don't ask me why, so this is just historical. And that gamma is characterized again with the eigenstate properties that the critical point is around 0.3. So here it is done in such a way, it's 1 minus gamma, so large gamma is weak disorder, small gamma is a strong disorder. What I am going to show you is how the system thermalizes. And my observable is this, what is called local temperature. I will not define it at this point of time, but you can imagine I can talk about small subsystems. So these are small subsystems of the size 2. And I can define a temperature there by looking at the density matrices. What you see here is the following. So it's a single configuration, and within a single configuration, so that's real space, that's time, logarithmic in time. And this is a weak disorder, that's a large disorder. And the color coded, it's in the following way, that when it is no color, that's the thermalization. That's the infinite temperature state. No feature, yeah? That's the featureless state. Initially, we start with a null state, a proper imbalanced state. And then what you see here is the following, that with increasing disorder, there are region which is large, has a strong color compared to white. So that means that the beta, or the inverse temperature, here is not yet 0. Yeah, so there is a strong block that slowly takes slow time in order to go to thermalization, whereas there are in between space, in between blocks, which kind of quickly thermalizes. Okay, this is kind of a scenario which tells you that even within a single configuration, if you look at cuts, if you look at positions, there are mixture of region which are cold block and the hot block. And that's interesting, and that I can show you with a cut. So this is essentially the cut. So this is the exponential decay of the temperature, or exponentially fast thermalization. So that's beta, the temperature for a given cut, J. So these are cut at 2, 4, 6, and different point in the space. So this is a weak disorder where system thermalizes, and this is the Floquet cycle. So I go for n equals to 200. And what you clearly see that there are exponentially fast thermalization, but with decay time, which is varied even within a given sample. Okay. So essentially, this is type of a form that you would expect, that there are time scales which has a J dependent. Now, if you go to larger disorder, similar feature emerges, and as you can see, the number changes 200 to 4000. It takes longer time to thermalize, with again the similar feature that there is a varied time scale that is present over here. Actually, if you average over this type of varied time scales, what you get is a stressed exponent. And this has been proposed many times with different models like avalanche models, and as well as, I think, resonance model, that you get a stretched exponent decay even for the autocorrelator actually, but it appears over here as well for ergodic phase of the transition. So essentially what you see here is the gamma, it's a weak disorder to a strong disorder limit, and then alpha, which is the stretched exponent, which has not close to 1, but very different than 1, but as it turns out that it depends on system size. Yeah. So we have shown it previously with Jens and Talia Lizama. She was a history student in PKS, that this exponent goes close to 1 as you increase the system size. Okay. How do we understand it? Previously, I told you that if you look at the static model, there is a way to understand all these timescales, these different timescales, by adapting entanglement as a time. And indeed, you can do it over here as well. So this is the same quantity, log beta. It's plotted against, not against time, but plotted against the diagonal entropy. So diagonal entropy is nothing but the rho nn log rho nn. It has a very nice interpretation because this diagonal entropy is essentially related, exactly can be mapped to the participation entropy in the Fock space. So this tells you how much the system expanded in the Fock space. So that's the participation entropy. So this has a one-to-one mapping. And what you see here, even we do not need to have a fitting parameter, all the curve collapses in a single scaling collapse. This is with the finite time, finite size data. This bending is essentially the page value where you will reach the thermalization, but overall, as you increase the disorder, the time scale is becoming more and more varied. It takes longer time to thermalize, but they thermalize in a similar way. So there is a scale invariance of dynamics that emerges without doing anything with the raw data. So these are our raw data. That also works, but that requires one fitting parameter. I wanted to even avoid that. So eventually thermalization means that this row will become diagonal, right? So the original row. Good, with this, I am at the end of my presentation. I will give you two essential messages, that there is coexistence of non-ergodic, ergodic grains that leads to this creep, this slow dynamics. So, but there is a flow towards ergodicity. I tell that, and I want to propagate the following idea also, that temporal dynamics can be conveniently parameterized by average entanglement flow, and that reduces fluctuation, reduces finite size effects, and also time effects, and reveals certain universal dynamics in these very interesting phase transitions. Okay, with this, I would like to thank you for your attention.
Okay, questions?
Thank you for the talk. So when you saw that the different sample spares within the, also with this entanglement time also don't converge to a single value. So what it signifies?
Sorry, can you repeat the question?
So when you saw that different initial sample states with time and in the entanglement time, it doesn't converge to a single value in the first part of your talk.
Here.
Yeah. So yeah, still it. Yeah.
So what it means is that the interpretation is the following. So here is the entanglement, proper entanglement, and that thing that kind of thermalizes that sample. These are different samples, means different configuration of disorder. All initial state is same. Yeah, but it tells you that this sample kind of goes to thermalization, means or imbalance goes to 0 for that sample. Also, it reaches page value, almost close to the page value. So it kind of maximally chaotic or ergodic. Yeah. Whereas that particular sample, you see the imbalance is almost finite. There is almost no decay of the imbalance. So if you just average over here properly, you will see that the W1.5 also doesn't thermalize. But we know that that value is much below the transition, okay, 20 forget, even below 3.5, right? So even there are samples which does not. It's just that there are varied time scales. There are different time scales, and I'm measuring that time by saying that the entanglement has not reached up to the page limit yet.
You're suggesting that averaging or with the normal time scale also don't show it thermalize.
Yeah, it won't show you. Yes.
Yeah.
Timeline you showed of WC, that kind of gave the impression that the main thing that shifts WC is the kind of diagnostic people chose to use. But from other talks, I also got the impression that part of the issue is about trying to extrapolate to large L. So how do the two pictures fit together?
My simple answer is the following. So usually if you want to do certain scaling, you need to be in the regime where your system is scale invariance already. You see that crossing point. We don't see the crossing point yet. Piotr is an expert on that. We always see shift in the crossing point of any observable you take, more or less, particular this type of observables. And also Lev worked on it carefully. That makes the scaling analysis very difficult. If you do not see that scale invariant point, at least let me tell you that in the non-interacting case, if we don't see it, we don't do scaling collapse. We just don't do it. So I don't know why. Okay, anyway, so historically we did it here. And that's why depending on which observable you look at, the shift is different for different observable. You see different numbers. But I don't think it makes much sense right now to do it. That's my opinion.
Sorry, I just wanted to comment that there are additional assumptions in the third scenario, right? So the first two were analysis of the microscopical models, and then there were some ingredients in those above induced avalanches scenarios added. So this also is, one needs to explore the validity probably.
Any other question? Okay, if not, let's thank Shaumo and close this session.